Welcome to this lecture in the ongoing series of lectures in real analysis. Last time what we proved was that suppose we have an interval I and we have an injective continuous function defined on that interval, then that function is strictly monotone, meaning it is either strictly increasing or strictly decreasing. So we'll use this today to prove something called the invariance of domain. These are the problems. And now let us get to the material of this lecture. So what we have is, first we have a lemma. What it says is that suppose we have a bijective continuous function defined on this closed interval a comma b, and well, its image will automatically be a closed interval because the image of an interval is an interval, first of all. That is the statement of the intermediate value theorem. And we also know that image of a compact set under a continuous function is compact, and the only compact intervals are closed intervals. So if we just take any continuous function defined on a closed interval, its image is automatically a closed interval. But what we have in the hypothesis is that it's a bijective continuous function, meaning it is an injective continuous function whose image is this. Alright, then we'll prove that its inverse is also continuous. Okay. So yeah, I mean, let's do this. So here is the proof, and there is no one way to do it. There are many ways to do it. I will do it in a way which I find most convenient given the material that we have seen so far, but you are encouraged to find your own proof. So what we want to show is we'll use the convergence criterion, that if a sequence converges, then its image also converges, etc. That criterion. So what we do is we fix. So let yn be a sequence in this such that yn converges to a point y, which of course belongs to c comma d. We don't need to even say that, but let me make a remark. So what we do is we pick a sequence in this which converges to a point y in this. Why I write this is just because any sequence, all of whose points are in a compact set, has its limit if the limit of the sequence exists, meaning if the sequence is convergent, then the limit of the sequence is also in that compact set. So we don't really need to say that y is in c comma d, but when we use the convergence criterion, what we do is we pick a sequence of points which converges to the same, in the domain of the function. We are interested in f inverse, and the domain of f inverse is this. Okay, so we picked such a sequence, and what we want to show is that need to show that f inverse yn converges to f inverse y. This is what we want to show, and this will prove continuity of f inverse by the convergence criterion of continuity. Alright, so let us write xn to denote f inverse yn and x to denote f inverse y. Alright, and assume on the contrary that xn does not converge to the sequence xn, meaning, let me write it this way, this does not converge to x. So we need to come to a contradiction. Alright, so if this convergence does not happen, so what does that mean? It means that thus there is epsilon greater than 0 such that xn minus x deviates by epsilon frequently. Which means that there are points, natural numbers n1, n2, n3 and so on, such that x and I minus x is greater than epsilon for all I. That's what this means. Okay. And now here is one statement that I will write and hope that you follow, is that passing to a subsequence and I will explain. Passing to a subsequence, we may assume that xn minus x is greater than epsilon for all n. So what have I done? What does this mean? As we saw, this means that there are points n1, n2, n3 and so on, such that x ni minus x is greater than epsilon for all I. So all I'm saying is that instead of using this sequence x1, x2, x3, just use, yn1, yn2, yn3, just pick, sorry, I should have written yn3. So instead of using this sequence yn, just use this sequence yn1, yn2, yn3. This still converges to y because the sequence yn itself converges to y, so any subsequence of that guy also converges to y. So we have this, and then we'll have xn1, xn2, xn3, where of course xn1 is the pre-image of yn1, etc. And this will deviate. This will satisfy that each of these numbers are at least epsilon away from x, or rather more than epsilon away from x. So we could have just picked the sequence. All I'm saying is that we could have just picked the sequence such that this does not just happen frequently, but it happens all the time. This is just for writing, proof writing convenience. And once we develop enough maturity, these statements, they don't bother us. We immediately capture what is the, what we are trying to say. So I hope this is not something that bothers you. If you are bothered by it, maybe first time, it is better to, actually work with the subsequence for which this happens, and the same kind of proof goes through as the one I'm doing. Anyway, so we passing to a subsequence, we assume that this deviation happens for all n. And now, since xn, this sequence xn is a bounded sequence being contained in the domain of f, we can pick a convergent subsequence. This is the Hine-Borel theorem. Every bounded sequence is a convergent subsequence. So let xnk be a subsequence of xn such that this thing converges. And let me choose the notation for the point of convergence, and let's say converges to a point t. Convergence to a point t. And where can t lie? T will also lie here, because each xnk lies in this closed interval, and as we saw that if you have a sequence of points in a closed interval, then if that sequence converges, then the limit of the sequence is also in the closed interval. In fact, you don't really need a closed interval, you just need a compact set for that property to hold. In fact, just a closed set, you don't even need a compact set. Anyway, so the point t, and we know that t will have to lie in a comma b. Alright. So now, by the continuity of f, we have f of x and k converges to f of t as k approaches infinity, because x and k converges to t as k approaches infinity, and continuity means a convergent subsequence, a convergent sequence is transferred to a convergent sequence by continuous function. So we have this is the convergence criterion of continuity. Okay, but this means, which implies that y and k converges to f of t as k approaches infinity. But since yn converges to y, yn k also has to converge to y. Any subsequence of a convergent sequence has the same limit as the parent sequence. So therefore, y equals ft, which implies f inverse y equals t, which implies x equals t. Okay. So we deduce that x equals t, but the thing is that x and k is at least, or rather more than epsilon away from x. Since this is happening for all n, this happens in particular for each nk. So x and k is at least, or rather more than epsilon away from x. So x and k cannot possibly converge to x. But x and k cannot converge to x. All k, and hence x and k does not converge to x, and this is a contradiction, because at one end we have x and k converges to t, which we have shown is equal to x, and at the other end we know that this convergence cannot possibly happen. So this is a contradiction, and we are done. So this contradiction proves that f inverse yn actually converges to f inverse y, and we are done. So that's it. So the proof is not hard, but it is also not as simple as the kind of proofs that we have seen so far. It's not, but it's definitely not a hard proof. Alright, so this is a lemma, and now we'll use it to prove something called which I at least would like to call the invariance of domain, because invariance of domain is a general theorem and it's a hard theorem, which is not in the scope of real analysis or even general topology. But anyway, so this theorem is called invariance of domain. This, the statement that I'm going to write is a very special case of the general invariance of domain. So nobody, I think, even calls the statement the invariance of domain. So let I be an interval. In R, of course. And f I to R be an injective continuous function. Let J be the image of I under F, and then we'll show that then the claim is that then F inverse going from J to I is also continuous. So since F is assumed to be injective, F is a bijection from I to its image, which is called J. So we can this makes sense, and the claim is that this function is a continuous function. So the above one is a special case where this interval I is actually a closed interval. The previous lemma is exactly that case. Here we are just saying we don't need to restrict to closed intervals. Any interval is fine. Okay. Fine. So I will not write all the details. I will argue via picture, but first we note a few things. So first we note that J is an interval. By the intermediate value theorem. Continuous image of an interval is an interval. This is one of the statements of the intermediate value theorem, as we discussed. Further, the function f is strictly monotone. This is what we proved in the previous lecture. Because f is a continuous, injective continuous function on an interval, hence it is strictly monotone, and assume that, without loss of generality, assume that f is strictly increasing. So basically we need to make two cases. One is the case where f is strictly increasing, the other is when f is strictly decreasing. The two cases are perfectly symmetrical, so we'll just argue with this. And we want to show that f inverse is continuous. We want to show that f inverse from J to, let me just write R, is continuous. And assume on the contrary that there is a point in J such that f inverse is discontinuous. And why not? So we need to come to a contradiction, and now there are two cases. So one case is y0 is in the interior of J. Recall this notation means the interior of J. And the other case is when y0 is not in the interior, which I will talk about, but first let's do this case. So both cases are exactly similar. So here we have, let's say, some point y0, and since it is in the interior of J0, we can find some epsilon such that this whole closed interval is contained in J. So there is an epsilon greater than 0 for which this, not just the open interval but the entire closed interval is contained in J. If that is a little bit confusing, what you do is you find some open interval which is contained in J. Because y0 is in the interior, such a theta greater than 0 exists, and what you do is you just slash it by half, and then this whole closed interval is contained in J, and this theta by 2 is what we are calling epsilon. So anyway, so there is some epsilon greater than 0 such that this whole closed interval is contained in J. So I don't want to draw it here, I want to draw it in the vertical line. Sorry about messing that up. So y0 is somewhere here, and there is some epsilon greater than 0 such that this whole pink thing is contained in J. Okay. Let us say that the pre-image of y0 minus epsilon is some point, let us call that A. Oops. And this has some pre-image. So let's call this A and this B. And the function may look like this. It is a strictly increasing function, so it may look like this. So what I'm saying is that take the pre-image of this guy, call it A. Pre-image under what? Pre-image under F. So F inverse of that is A and F inverse of that is B. And F, one can depict F like this. It's a strictly increasing function. Alright, but now what we have is, just restrict your attention to this closed interval. We have f taking this closed interval to that closed interval in a bijective fashion. And f is continuous, so f is, when you restrict it to this closed interval, it is again a continuous function. So what is happening is we have this continuous function f restricted to a comma b, going from a comma b to, well, this pink interval. Let me just draw a pink interval. I hope you understand by this I mean that I don't want to write so much. Alright, so what this says is that if you apply the previous lemma now, you know that the inverse of this function defined from this to that is a continuous function. So therefore, by previous lemma, f inverse, or rather let me do the full thing, f restricted to a comma b, and you invert it, then you'll get the pink interval as the domain, and in the image of this function is precisely that. So this is continuous. Okay, and therefore I mean, this is, I shouldn't be saying this, but okay, so what this means is f restricted to, this is same as f inverse restricted to a comma b. This going to, not a comma b, but the pink thing. So all I'm asking is for you to verify this. This is a very trivial statement. It just looks complicated. It's that inverting the restriction is same as restricting the inversion. Basically, if you pick a point here and you take the inverse and go here, that is same as applying the inverse of this function to that point. This is a tautology, so I'm struggling with it, but I hope you follow this. But which means that if you take this function, f inverse restricted to this pink open interval, going from the pink thing to let me write r, this is also continuous. So what is this? This is denoting this open interval. Let me write it so that there is no confusion. By this pink thing we mean y0 minus epsilon, y0 plus epsilon. This is what that means. So this is continuous. So the restriction of f inverse to this open interval is continuous. But continuity is a local property. If you've shown that the restriction of f inverse to a neighborhood of y0 is continuous, then f inverse is actually continuous at y0. To detect continuity, you just need to observe the behavior of the function in neighborhood, any neighborhood of the point in contention. So all of this long kind of thing is probably just confusing rather than helping. But all I'm saying is the following, that what we did was, we picked a point y0 and j0 where we assume that continuity of f inverse fails. Then we picked a neighborhood around that, rather a closed interval around that, which is contained in j. We can do that because of this assumption. And we just said that, okay, forget everything about the function f, just focus on this part where a is the pre-image of this guy and b is the pre-image of that guy. Just observe the behavior of the function f in this guy. And to argue continuity of f inverse, it is enough to argue continuity of f inverse in this open set, because continuity is a local property. By the previous lemma, we have this leverage that f inverse is continuous when restricted to this closed interval, and hence when restricted to this open interval. That's all this is saying. So I hope I did not confuse anyone with all this argument. And case 2 is exactly similar. Case 2 is y0 does not belong to the interior of J. What does this mean? This means that y0 is an endpoint of J. So this means that so there are this has further two cases. One is that infimum of J is y0, and the other is supremum of J is y0. Just convince yourself that these are the only two possibilities because J is an interval. If you have a point which is not in the interior, then one of these two must happen. And then exactly the same kind of argument will go, and I leave the details to you. Instead of having a full neighborhood, you will have a half neighborhood. But that's okay. That doesn't really, disturb the argument because you'll be doing the exact same thing as you did here. Anyway, so that's it. I think. Oh no, so there is one application of this. So here is a very nice corollary. Let n greater than equal to 1. Then the map which takes x to x to the power 1 by n is continuous. So how do we show this? I mean, just take n equals 2 and see that this is saying the square root function is continuous, and that's not something that we've seen so far. You can prove it directly, but the above theorem, gives you a very, very soft proof of it. You don't need to find any estimates. Just a very simple, straightforward argument. So here is how we do it. So define f as a map which takes x to x to the power n, and we have already seen that this is a continuous function because after all this is a product of a bunch of continuous functions. This is a polynomial restriction of the polynomial x going to x to the n to this part. So this is a continuous function, and this is in fact injective, and hence it is surjective on its image, but this is precisely the image. So this is a bijective continuous function. Then f is a bijective continuous function. We saw this in fact. Why is f a bijection? We saw using the intermediate value theorem. Bijective continuous function. And this is an interval. This is this interval, which is, suggestively, this is like this. 0 and it does not end. So this is an interval, and hence the inverse function, which will take this to that. And what is the inverse function? It just takes x to the nth root, is also continuous. And that's it. So it proves continuity of these folks. So that's it. That's all that I wanted to do today. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.